Hello, welcome all to this new reading group session organized by Continual AI. Today we have the pleasure to host Kai Wang from the Computer Vision Center in Barcelona. That's right, Kai, right?
Totally right.
And yeah, and he is going to present his recent work, ACAE-REMIND for compressed feature replay for online continual learning. And I'm excited to learn more about this topic because I think that is tapping into a very interesting research direction or let's say latent replay for a scenario that is now starting to become more and more, I would say, investigated, where examples are processed one at a time or at least on small batches of data. So thank you so much, Kai, for being here. And without further ado, the stage is yours.
Okay, thank you. It's my honor. So should I begin now or?
Yes, absolutely.
Okay, so could you see my screen now? Yeah.
Yes, I can see your screen. If you want, you can present full screen. Okay. Yes, and we should be able to see it. Right, perfect.
Okay, so everyone, very happy to be here. It's my honor to be invited to make the presentation about my recent work for online continual learning with ACAE-REMIND for compressed feature replay. And so in the first slide, I will give a broad view for continual learning because in Continual AI, we have had a lot of workshops and a lot of talking about these different papers. And so here I classify them into different branches from the machine learning approaches. Actually, in most cases, people are caring about the supervised continual learning. And in the supervised continual learning, we have different tasks like classification or semantic segmentation or instance segmentation. Actually, for most of them, we have talked about some of them in the previous workshops. And then there are also other topics like unsupervised continual learning, which is related to GAN or representation learning. And in recent years, there are also some semi-supervised and reinforced continual learning. And some of them we have also talked about that in the previous workshops, and also the topic model and meta learning. So it's that a broad view, which we will maybe in the future work we will consider. Okay, so for my job in my recent work, I was only considering on the classifications, and in classifications we have something we should consider. First is that whether our learning is online or offline, and whether the task is known or unknown in the test time. And so in my this recent paper is online and task-agnostic. That to let you know that's the basic setting instead of in case that you have some confusion. Okay. So the contents in my slide is divided into 3 sections, and the first is the motivation, and then I will introduce my ACAE-REMIND model, and then the last section is for my experiments. Okay. So what's the motivation? Actually, a very huge branch in continual learning is the replay based, and some people did the image replay to overcome forgetting, and some recent paper did feature replay, and no matter what it's image replay or feature replay, they could also be classified into the fake replay and the real replay. For the fake replay, it means that we generate some images from the GAN or a version of auto-encoder, and for the real replay, it means that we save some true features or true images from the previous tasks to make it beneficial for overcoming forgetting the future tasks. So here I made a very simple comparison between the GFR, which is a generative feature replay from Xiaolei Liu, and the REMIND is online continual learning in ECC 2020. And then it's our proposal. We made the comparison among the replay layers and the compression ways, and whether it's online or offline. Okay. So, and from our observation, there is a problem in the replays that if we do the feature replay, sometimes we need to fix some layers in online continual learning setting, which is true in the Remind paper. We would find that if we fixing more layers, the model will be less optimal for the continuous task. So here is our analysis from the experiments. Okay, so first our first task is learned on 50 classes and on 10 classes. On 50 classes and on 10 classes, and the comparison is made by these two curves. You can see that if we pre-trained on 50 classes, the drop is really small compared with only 10 classes. That's very true and very reasonable to our intuition. So you can see that if we have a very huge first task, that means that we could learn a very good backbone. Well, if we only have 10 classes at the first task, the backbone will be learned not that optimal. So that's the problem that exists in this case. Okay. And so here we can see that in block 2.0, the drop is much smaller in the lower layers for the pre-trained model on 50 classes, and it's much bigger for the pre-trained model on only 10 classes compared with the joint training upper bound. And then in block 4, you can see that the drop is from almost 80 to 60 for the pre-trained model on 10 classes, and it's only maybe no more than 10% for the pre-trained model on 50 classes. Okay, this is a more concrete comparison on this case. And then here I will briefly talk about the remind method, which in our paper we are based on. Is that in the remind method they are replaying the features in the intermediate layers of the model. Actually, in their model, they will replay the features from block 4.0 in ImageNet-18, which is the last block. And in this case, they will pre-train their model with a very huge first task, that means that the feature extractor has been learned very well with a great bunch of data. So they won't have, so in this case they won't have the problem that the feature extractor is not that good as we suppose it to be. So I just listed some drawbacks here, which why it's not that good, and what's the drawbacks we could improve in our work. So here I simplify listed our ACAE-REMIND method by two stages. The first is individualization stage, which is similar to the remind, but then the individualization stage is still very different from remind. Is that we insert the ACAE training, which means the auxiliary classifier auto-encoder, and then with the PQ training. And after this initialization stage, we will use the feature extractor as the backbone and the ACAE to replay the features in online continual learning stage. Okay, so here is just a brief talk about that. Later I will show you the illustrations by figures. Okay, so for the initialization stage, first we will learn the classification model with the first task. And under this case, we were doing the conventional classification learning with the cross entropy loss, which we are all I think is very familiar, so I won't talk too much about that. Okay, so here is the illustration is the ImageNet-18, and there are 4 blocks, and each block is further split into two parts. Okay, so after the feature vector, there is a GAP, which is a global average pooling to extract the features. Okay. Then in the second stage, we will insert the ACAE into the blocks where we want to replay the features. Okay, so if we want to replay the features, for example, if we want to replay the features in block between block 1.1 and the block 2.0, you just insert this module there, and you train the auxiliary classifier auto-encoder with the reconstruction loss and the classification loss. And by this way, the reconstruction loss is to ensure that the features are reconstructed very correctly, not that far away from the original feature. And the classification loss is to ensure that the features are discriminate as the true features. Okay, so this section is ACAE training, and then in the third part of the initialization stage is the product quantization training. And the product quantization is composed of the PQ encoder and the PQ decoder. And so here, this PQ is also trained with the reconstruction loss. Okay, so the PQ is taken from the product quantization paper, which is from, I think, from INRIA. Okay, and then in the next stage, after we have learned all this, all what we need for the online continual learning stage, I mean the backbones and the ACAE and the PQ, we will do the online continual learning with fixing all the previous layers, that including the previous blocks, the PQ encoder decoder part, and also the auxiliary autoencoder. Okay. And then in the training stage, we will do some resolver sampling, which is sampling some exemplars from the resolver to help training the later blocks. Okay. And then in the last section is talking about our experiments. Okay, so for the experiment, we have 3 different evaluation metrics. First is AOC, which is the brief item about the average accuracy over classes, and the AOT is the average over tasks up to the current task, and the last, it means the top 1 accuracy after learning the last task. And we why we take these 3 metrics is that we found in some papers they have different metrics, so we just integrate all of them to see what would happen in our case. Okay, so the first experiment is on ImageNet-Subset. We have listed the exemplar information that including the number of exemplars and the shape. It means the dimension, the features of images, and the total memory, and that is, to shorten the memory usage is also one of our purpose of ACAE-REMIND. So we just throw them all here, and by the comparison in the right part of this table, we could see that on ImageNet-Subset, our method could get a better result with the replay on blocks 3.0, and we get by average, I think is 0.5, 1, and 2.5% compared with the original Remind. And we could also see the increase of the performance from the replaying from block 1.0, block 2.0, and block 3.0 under the second column setup. And yeah, and by this case, we could see that our memory usage is only 51 megabytes compared with the saving images. Saving images is 301 megabytes. Okay, and we could also see that our methods are very close to the offline continual learning method, and yeah, that's what we could gain here. And the next slide is about the experiments on CIFAR100. We got a similar table structure as the ImageNet-Subset, and we could see similar trends as we could observe on ImageNet-Subset. And then here we could also see the similar trends that we are increasing the performance from lower blocks replay to higher block replay. And it got similar performance compared to the offline method. And okay, and another thing, sorry, I need to go back. And another thing we need to notice that these 2 settings are beginning with 50 classes at the first task, and then split them into equal equal tasks into 5 or 25 or 50 steps. And yeah, that's one of the settings which we did in the paper. Okay, so with the 50 classes as the first task, what we could get is a very good backbone. So in this case, we don't need to worry about that whether the feature injector is good or no. So the replay on higher blocks could benefit from that, because in ResNet 18, the higher blocks are with smaller feature maps. For example, in ResNet 18, the last block contains the features as 2048 multiplied by 7 by 7, and then in block 3.0 is the feature map size is a little bit bigger, it's 14 by 14, and then in the block 2.0 is 28 by 28. So that means if we want to replay on the lower blocks, we cannot replay as many as features if we are doing the online continual learning under the same memory buffer limitations. So what I just gave now is some explanation to why this could happen here. Okay. So then the next step, we did another setup, is that we split CIFAR100 into 10 equal tasks, and each with 10 classes. And that's different from the previous setup. We see that 50 classes as the first one. And so here we could see the benefits from our replay on block 1.0 instead of other blocks, because we could see that with our replay on 1.0, it's much higher than the remind replay on block 4.0, and it's much closer to the BIC, which is to some way the upper bound under this case. And we should notice that on the left column, the ICAR, RPS, NET, and BIC, all of them are offline methods, and they say they were using more memories compared with our method. So you could see that remind fails a little bit on this under this setting, and our method got similar results as the state-of-the-art method BIC. Okay. And then the last experiment is on CIFAR10, where we split equally into 5 classes. We did that because in some online continual learning methods, they were doing on small data sets like MINIST and CIFAR10. So here we just illustrate just to find out how was our model working under this case. And we could also see that our method got the best. Yeah, and we're saving more because under this case, we are using the same memory buffer and saving more features because of our auxiliary auto-encoder. We have compressed the features into a small size. Okay. Okay, so here I will show whether there are some conclusion about the replay block for the features with auxiliary classifier auto-encoder. And so here we made the comparison under these 3 different settings. The first one is ImageNet-Subset with 50 classes, and the second is similar to second on CIFAR100 is similar to ImageNet-Subset. We could see still 50 classes, then equally split into 5, 25, and 50 steps. And then on ImageNet-Subset, we split them into 10 classes and then 9 steps. And then we made the comparison. We could see that if the first task is with 50 classes, the replay can always benefit from replay on the Peltimate blocks. From the figure A and the figure B, we could see that the performance get increasing from block 1 to block 3 and then drop on block 4. And from figure B, we could see that it's increasing to block 2 and then drop to block 3. But if the first task is with required classes, we could see that it's dropping from block 1 to block 4, which means that the replay blocks, it also depends on how was our first task. In another way, we should say how was our feature directors, whether it's very good. If it's very good, we could be more confident to play on the higher blocks. Otherwise, we should play on the lower blocks. Okay. And so here we have we showed some conclusions from our paper. The first we just analyze the drawbacks of freezing the backbones, and then we show that if the first task is with very rare classes, the replay should be lower layers, and then based on these intuitions and observations, we improve the remind paper with our auxiliary classifier auto-encoder. And actually, yet in the future, we should also consider how to solve this problem in some other ways, how to do the compression more optimally. So, okay, that's all these things. If you have any questions, yeah.
Thank you so much, Kai, for your very interesting presentation. And we have already one question in the chat. Okay. Lucas says, in your experiments, how many items are in a single codebook? 256 or?
Sorry, I don't have the slide number. Could I go and you say stop? Yeah. Okay, which chat?
Hi, can you hear me?
Yes, we can. Yeah.
So my question was more general to all your experiments. So I think in different scenarios, you're always doing vector quantization. I was just curious, what is the number in general of these codebook items within a single codebook?
Okay. So, for example, here in this slide 17, if you can see my screen, okay. Okay. So here we have shown that the shape is CHW. It means that the channel height and weight. Actually here it means that we need to replay the features is 7 by 7, and we have 8 code books. Actually, the 8 is the number of code books, and for each code book, there are 256 items in the code book. And so the code book is really very small, and so for indexing the code book, you only need 1 byte to index to that, because it's 258. It's the power number of 2 multiplied by 8 times. Okay, so I don't know whether you could get it. Yeah.
Yeah, that answers my question. Thanks.
Okay.
So, Kai, I have also a question. So, do you see any issues with respect to the scalability of this technique? I mean, do you think that this fixed number of code books would work on any possible situation? I mean, do you see any limitation? Do you see how we can have them incremented maybe over time? I don't know, some ideas around these topics.
Okay, got it. Actually, the code number is, I have to say that the code number, of course, if you have a bigger code number, you got better results. But in some cases, you should compress the code books, the number of code books, depending on what you want. Actually, in my experiments, the preliminary experiments, I found that if I go much lower with rare code books, the drop or the performance it decreased very fast. So finally, I decided to use these numbers because I found that this number performs very well under this case. Actually, in slide 17, you can see that with 8 code books, it's the second row. It's 8 by 7 by 7. You can see that the increase from 60 to 70 to 32 with our replay on 1.0, 2.0, and 3.0. You can see that 72.58. It's almost a 12% increase compared with 60.70. But if we have 32 code books, like in the last row, we see that 32 by 7 by 7, the increase is from, there's no increase anymore. Actually, because under this case, you have, you can say, you can more precisely replace the lower block features. You can see that they got similar performance with 74.08 and 73.75 and 73.63. You see that the difference of the code books. That's how that influenced the performance. Yeah.
It makes sense. Thank you so much, Kai. Do we have any more questions for Kai?
Hi. Yeah, I have one more question if the floor is open. So when you're calculating the total memory usage, are you accounting for the extra parameters that come from the autoencoder?
Yeah, actually, what you said is right. Actually, at the beginning, I should calculate that, but because of the autoencoder, it's a 2-layer mapping. It's too small. It's just no more than 1.1 megabytes. So under this case, we didn't include that inside. Yeah, I think that could be neglected because compared with the memory buffer, which we use to save images or features, it's quite too small, maybe no more than 1%. So I just ignore them. Yeah.
Thanks.
Great. So if we don't have any more questions to Kai, then I think we're in a good moment to just remind that we have a new reading group session coming next week at the same time with Tyler Eyes presenting her work with great researchers at the intersection with neuroscience. It's going to be a paper about replay in the brain and what we can learn from new insights in that area. So you're invited to join. Also, I invite Kai to share his slides with me if we can, or directly post them on our forum so that all of us can access to these interesting results and your presentation, Kai. And then I wanted also to invite you, Kai, to maybe contribute to Avalanche with these. I hope you already know about this, but within ContinualAI, we are developing like this library for continual learning, and I guess it would be very nice to see your own strategy implemented into the tool. So feel free to reach out to us and the rest of the maintainers in case you want to contribute to that as well.
Okay. Of course, I know it. Yeah.
Great.
Thank you for your
invitation. Yeah. And I hope you will use it in your next paper. But yes.
Okay.
So thank you all for joining again, and I'll see you next week. Bye.
Okay. Thank you so much. See ya.